Welcome to the deep dive. We're taking a look today at something really interesting happening with those super smart large language models.
Uh-huh.
You know how they've gotten so good at figuring things out? A lot of us thought it was because they were doing this detailed thinking as they came up with answers, almost like showing their work.
Exactly. Yeah,
Yeah.
we've seen these models generate, long chains of thought,
Hmm.
even looking back at their own steps, maybe correcting course
Right.
and checking their reasoning before giving a final answer.
Hmm.
It really seemed like that detailed process was key to their problem-solving skills.
But hold on, because some brand new research is making us, well, question that.
Mm.
What if all that intense mental gymnastics isn't actually as necessary as we believed?
Right.
That's the core of a fascinating paper we've been digging into. Reasoning models can be effective without thinking.
Yeah, and it's quite a title.
It is. And get this, the truly surprising part is that this simpler approach actually performed just as well, if not maybe even better, in many cases.
It really challenges what we thought we knew.
Totally. Everything we thought about how these models work.
It really does. This paper kind of throws a wrench in the widely held idea that this drawn-out thinking process is, essential for LLMs to reason effectively.
So our mission here.
Well, our goal in this deep dive is to unpack this unexpected research and really get a handle on what it means for our understanding of AI and how it reasons.
And our main source for this exploration is, of course, that eye-opening paper. Reasoning models can be effective without thinking.
That's the one.
Okay, so let's dive in. This whole concept of LLMs thinking. The paper describes this traditional method they call thinking. Can you maybe paint a picture for us of what that looks like under the hood?
Certainly. So the thinking process, as we've generally understood it in, let's say, advanced LLMs, involves the model generating a lengthy sequence of words or tokens, as they're called.
Right, tokens, the building blocks.
Exactly. Think of them as the basic building blocks of language for these models. And this sequence is meant to mirror sort of human-like reasoning, breaking down a complex problem into smaller, more digestible steps.
Okay.
You might see the model explore different possibilities, think about the results it's getting along the way,
Hmm.
maybe even backtrack if it realizes it's gone down the wrong path.
Like self-correction.
Precisely.
Mm.
And ultimately double-check its work before presenting the final answer. The paper even has a diagram, figure 1, showing this as a thinking box, where all this internal reasoning happens before the final solution pops out.
Right, I saw that, the blue box in figure 1. It's like the model is saying, all right, here's my internal monologue as I work through this.
Uh-huh.
And then the paper introduces this totally different way of doing things called no thinking. How does that work? It almost sounds, well, too simple.
Well, it's certainly more direct. The no-thinking approach, illustrated by the orange box in figure 1, basically skips this whole detailed reasoning process.
That's it, just
About that.
gone.
Pretty much. The researchers did this by using very simple prompts. They essentially pre-filled the beginning of the model's response with a dummy thinking block. It's almost like a placeholder.
A placeholder? Like,
A perfect example they give is thinking. Okay, I think I have finished thinking.
slight laugh. Seriously. That's it.
That's it. And then the model just, well, it jumps straight to the final answer. No actual step-by-step reasoning is generated in between.
That's wild. So it's like telling the model, just pretend you thought really hard about this and now just give me the solution.
You could kind of think of it that way, yeah.
And the truly mind-blowing part is that the research discovered this not thinking method could actually perform just as well, and sometimes even better than the traditional thinking method across really hard tasks.
Yes, exactly. Across a wide range of seriously challenging reasoning tasks. We're not talking about easy stuff here.
Like what kinds of tasks?
Not at all simple quizzes. The researchers rigorously tested these methods on 7 different, very demanding reasoning data sets. We're talking about mathematical problem solving at the level of the AM and AMC competitions. The kind of math that would stump most of us.
Oh, yeah, definitely.
And even tackling parts of the Olympiad bench,
Hmm.
which is significantly more advanced.
Wow.
Plus, they also looked at coding challenges with live code bench and formal theorem proving using Minif2F and ProofNet.
So a really thorough evaluation across different kinds of reasoning, not just math.
Very thorough, yes.
And how did they actually measure how well the models were doing on these different types of problems? What was the metric?
Good question. The main way they measured success was using something called pass at K.
Pass at K. Okay.
This basically tells us the probability that at least one of the top K answers generated by the model is correct.
Ah, Okay, so if K is 1, it's just, yep, did it get it right the first time?
Exactly, standard accuracy. But as K increases, it accounts for the scenario where the model generates multiple attempts, and we maybe pick the best one. So a pass at 5 of 80% would mean if the model tries 5 times, there's an 80% chance at least one of those tries will be correct.
Okay, that makes sense. So what were the main results when they compared thinking and NoThinking without any limits on how many of those tokens the model could use? That's shown in their figure 4, right?
Yes, Figure 4 gives us a great overview of those initial findings. And what's really interesting is that on the formal theorem-proving datasets, Mini-F2F and ProofNet,
Uh-huh.
NoThinking performed just as well as thinking across all different values of K,
Just as well.
just as well. And it did so while using significantly fewer tokens, about 3.3 to 3.7 times less.
Wow, 3.7 times less. That's a massive difference in efficiency right there.
Huge.
Absolutely. What about the other finding, which seems maybe a bit more intuitive? That NoThinking wasn't quite as accurate as thinking on the very first try at K1 for some of the other data sets?
That's correct. On datasets like AIM, AMC, Olympiad Bench, and LiveCode Bench, NoThinking often started with a lower accuracy when looking at just the first generated answer.
Okay.
However, the really fascinating trend is that as CRES increased, meaning the model generated more attempts,
Right, more tries.
NoThinking would often catch up to and even surpass the performance of thinking.
Surpass it, even starting behind.
Sometimes, yes. And it was still using those significantly fewer tokens, anywhere from 2.0 to 5.1 times less.
Still way more efficient.
Much more efficient. They also included another model, QuinInstruct, as a comparison, and its performance varied quite a bit depending on the specific data set.
Interesting. So even though NoThinking might not nail the answer on the very first try as often, it seems to really benefit from having multiple attempts.
That seems to be the case.
But what happens when you make sure both methods have the same brain power to work with, in this case, the same number of tokens?
Right.
That's where this idea of budget forcing comes in, as shown in figure 5. It's like seeing what happens when we give both methods the same amount of, well, thinking time, token-wise.
Exactly. To really understand the efficiency gains, the researchers used this budget forcing technique. This essentially limited the total number of tokens that both thinking and NoThinking could generate.
Okay, level playing field.
Kind of.
Okay.
And the results here, shown in figure 5, are quite compelling. In low-budget scenarios where the token limit was relatively small, say, fewer than around 3,000 tokens, NoThinking generally outperformed thinking across all values of K.
Outperformed it, even on a budget.
Yes. And what's even more interesting is that this performance gap tended to get even bigger as K increased.
So when resources are limited, skipping that long thinking process seems to be the more effective way to go, especially if you can generate multiple attempts.
That's a key takeaway, definitely.
Okay.
Now, when the token budget was higher, say around 3,500 tokens, the situation became a bit more complex.
How so?
Thinking sometimes performed better at pass at 1.
Ah, on the first try again.
Right. Suggesting that if it has enough resources for that initial detailed reasoning, it might have a slight advantage in getting the first answer right.
Makes sense.
However, even in these higher budget situations, NoThinking quickly caught up and surpassed thinking, starting from when the model generated 2 or more attempts. So K2 onwards.
Got it. So even with more resources, NoThinking pulls ahead if you allow for more than one shot.
Pretty much, yeah.
This really highlights that balancing act between accuracy and how many resources you're using, which they show us in figure 6. It's not just about getting that single perfect answer right away.
Precisely. Figure 6 plots the pass at K against the average number of tokens used. And what we see is that for pass at K, where K is greater than 1.
So multiple attempts.
Yes, multiple attempts. NoThinking consistently outperformed thinking across the entire range of token budgets.
Consistently better.
Consistently better for K1. For pass at 1, as we discussed, NoThinking was better when resources were tight.
Low budget.
But thinking could have an edge when there were more resources available.
High budget.
Except for those coding challenges on LiveCode Bench. That seemed to be an exception there.
Okay, so NoThinking can be more accurate, especially when you consider generating multiple attempts and you're working with limited resources. That's clear. But what about the practical side? Speed, efficiency in, like, real-world apps.
Right, that's crucial. This is where the fact that NoThinking often uses so many fewer tokens becomes really important.
Because less means faster.
Exactly. Because it's generating less text, it naturally leads to lower latency.
Latency, so faster response times.
Faster response times.
Yeah.
which is critical in many applications where users expect quick answers and, aren't willing to wait around.
Yeah, nobody likes waiting for the spinning wheel.
Precisely.
Yeah.
And because NoThinking uses so many fewer tokens, that has a direct impact on how quickly it can generate an answer. Less waiting around for the user.
Makes perfect sense. Fewer tokens to generate means less time spent generating them. But the paper also discusses this concept of parallel scaling with no thinking. What's that all about?
Right, so building on the finding that NoThinking really benefits from generating multiple responses.
The K1 thing.
Exactly. The researchers looked into parallel scaling. This involves generating multiple independent responses at the same time.
At the same time, how...
Think of it like having a team of AI assistants all trying to solve the problem simultaneously,
Okay.
and then we just pick the best answer they come up with. They call this using best-of-n methods.
So instead of one long, drawn-out thought process, you have multiple quick attempts happening simultaneously, and then you just pick the best one. How does that impact the speed?
Well, because these generations happen in parallel, the overall time it takes to get an answer is mostly determined by how long it takes for the slowest of those parallel attempts to finish.
Ah, not the sum of them all.
Not the sum, no, not like adding up all the steps of a single sequential thinking process. This can lead to really significant reductions in the time it takes to get a final answer for the user, much faster overall.
And what were the results of this parallel scaling approach? Figure 7 and tables 2 and 3 have some really interesting data on this, right? I remember looking at those.
Absolutely. Figure 7 clearly illustrates that NoThinking with parallel scaling often provides a much better balance between accuracy and speed compared to thinking,
Better balance.
whether thinking is also done in parallel or not.
Okay.
And for tasks where you can perfectly verify if an answer is correct,
Yeah.
like informal theorem proving with Mini2F and ProofNet.
Where you know for sure if it's right or wrong.
Exactly. NoThinking. With parallel scaling, not only outperformed thinking in terms of accuracy, but did so with a remarkable 7 times lower latency
7 times.
and used 4 times fewer tokens. That's highlighted in Table 3.
Wow.
That's a potential game changer for those kinds of tasks.
That sounds like a huge win for efficiency. What about those tasks where you don't have a perfect way to automatically check if the answer is right? Like maybe the math problems.
Good point. For those situations, they use strategies like confidence-based selection, where the model itself kind of indicates how confident it is in its answer,
Okay. The model rates itself.
and also majority voting among parallel responses.
Ah, like democratic AI.
Slight chuckle, sort of. And Table 2 shows that NoThinking with parallel scaling consistently outperformed thinking with parallel scaling across most of the math problems they looked at.
Consistently again.
Yeah. For example, Olympiad Bench, NoThinking, achieved higher accuracy on the first try, pass at 1, with a 9 times lower latency compared to the full thinking process.
9 times lower latency. That's huge.
It's very significant. They did note that Live Code Bench, the coding one, was an exception where NoThinking wasn't quite as effective.
Why was that?
Well, they suggest it's possibly because it's harder for the model to reliably assess its own confidence on coding tasks compared to, say, math.
Ah, okay. Coding confidence is tricky.
Seems to be.
So for a lot of reasoning tasks, it looks like this no-thinking approach, especially when you combine it with generating multiple attempts at the same time. Parallel scaling could be a much more efficient and faster way to get really good results.
That's a solid conclusion based on the research, yes.
Yeah.
They also briefly looked at something else, how diverse the answers generated by thinking and NoThinking were. That's in Table 1.
Right. Diversity. What did they find there?
They found that NoThinking tended to have a more consistent level of diversity in its answers across different questions compared to thinking.
More consistent diversity. What does that mean exactly?
It means the spread, or variety of answers it produced, didn't vary as much from one question to the next. Thinking might be very diverse on one question and less so on another, while NoThinking was more steady.
Okay. And why might that matter?
Well, they suggested that this consistency might be one of the reasons why its performance when generating multiple answers, the pass at k, improves so much as k increases.
How?
It implies perhaps a broader exploration of the solution space, even if individual attempts aren't always on the right track initially. More consistent exploration might mean you hit the right answers sooner within your k attempts.
Interesting. So it's exploring different angles more evenly.
It's an interesting observation. While the average diversity wasn't always higher for NoThinking, the fact that it was more consistent suggests that it might be exploring the possible solutions in a more uniform way.
Which could help find a correct answer within those talk case samples.
Exactly. However, the researchers are careful to point out that diversity alone doesn't completely explain why no thinking performs the way it does. It's likely part of the picture, but not the whole story.
Got it. So to wrap things up then, what's the main surprising takeaway from all of this, the big headline?
I think the most surprising result, really, is that this explicit thinking process, the step-by-step reasoning that we often see in today's most advanced reasoning models, might not be as absolutely necessary for achieving high performance as we, well, previously thought.
That it's maybe optional in a way?
Or at least not the only way. This no-thinking approach, which essentially skips that detailed internal reasoning, can be remarkably effective. That totally flips the script on how we thought these powerful models worked.
It really does. And what are the big implications of this research? What does it mean going forward?
Well, the research strongly suggests that combining no thinking with the ability to quickly generate and check multiple potential solutions, this parallel testing approach, has significant potential for achieving much better accuracy and speed, especially when computational resources are limited.
Budget constraints.
Or when getting answers quickly is really important. Low latency scenarios.
Right.
It really makes us rethink whether those long step-by-step thinking processes are always the best way or the only way for LLMs to operate.
So for you, the listener, trying to get a quick answer from an AI, this no-think approach could mean a significantly faster response time, less waiting around.
Potentially, yes.
Yeah.
A much faster interaction.
Okay, so the key thing to remember is that large language models can be surprisingly good at reasoning without going through these long step-by-step thought processes, particularly when you pair that with the ability to quickly generate and check multiple potential solutions.
Precisely. That sums it up well. And this leads to a really thought-provoking question for you, our listener.
Ah, the takeaway question.
Indeed.
Yeah.
What are the wider implications of this for how we design and use AI systems? Could focusing on more direct solution generation in certain situations lead to more efficient and faster AI without sacrificing accuracy? And maybe even more fundamentally, how might this change our understanding of what reasoning even means when we're talking about artificial intelligence? Is it the process or just the result?
Some truly fascinating food for thought there. If you're keen to delve even deeper into this, we highly recommend checking out the research paper itself. Reasoning models can be effective without thinking.
Definitely worth a read.
Thanks for joining us on this deep dive.